technical advisor, Vasantdada Sugar Institute, Pune. He is going to make presentation on heat and mass balance case study of Cogen Plant. A brief introduction of the speaker. He is BE Electrical and distinction from COEP, Pune in 1974. Experience. He has got 8 years experience in sugar factory, about 1 year in textile industry. He was joined at Deccan Sugar Institute, Pune in 1982. Name changed to Vasantdada Sugar Institute, Pune. Rendered extensive technical services to member sugar factories of VSI, teaching training to sugar engineers and sugar technologists. Presented more than 50 research papers at various seminars. Attended conventions of DSTA, STI and ICCT during 2001 at Australia and during 2003 at Hyderabad. Prepared a DPR, detailed project report, for new sugar factory, expansion of sugar plant and modernization of sugar plants for reduction in steam and power. He was a team leader for the survey and recommendations of government and to Kilari Sugar Factory after the earthquake. He was active for 28 years at VSI and retired as a technical advisor from the year 2010 after 3 years extension. Now he is active for technical services to sugar and allied industries. Till to date, he has got total technical experience for 50 years. Now I request Mr. Borude to start his presentation.
Thank you, Mr. Srikanth. So this is the importance of the heat mass balance. The study of the heat mass balance helps to energy efficiency. I have a vision problem. Next slide. So the case study of 5000 TCD proposed sugar plant with 3 cases. One is a Cogen plant with a plain back pressure turbine, double extraction back pressure turbine, and triple extraction condensing turbine. So the comparison of these 3 cases is worked out, and I have displayed here the case of triple extraction condensing turbine. The fiber percent is considered as a 13.5. Bagasse moisture is considered as a 49%. Bagasse pole is 2%, and for calculation of bagasse percent, 77% is the purity of the last extract juice. So this total bagasse is calculated. The bagasse used for the bagasse oil is 0.8%, and for stoppages 1.5% bagasse is considered. So the bagasse production is 68 TPH, and 58 TPH bagasse is available considering the use of bagasse oil and stoppages. Next. Then here the calorific value or heat energy in the bagasse is mentioned for moisture of 49%, 2% pole, and GCV 2322, and net calorific value 1850. So the thermal efficiency of the boiler is calculated. There are 5 major losses. Out of that, 2 can be calculated and 3 losses are estimated. One is the condensation loss, second is the sensible heat loss, then unburned solid loss, and radiation loss and incomplete combustion. So out of this, the major loss is condensation loss, and that is different between GCV and NCV, and this depends upon the moisture of the bagasse. This is about 20%. The next loss, calculated loss, is the sensible heat loss. This sensible heat loss depends upon moisture in the bagasse, excess air ratio, and flue gas temperature after last heat recovery unit, that is air preheater, and also some on ambient temperature. So this figure is 140 kilocalories per kg of bagasse, and this percent is 6.45. So these are the 2 major losses. Then the unburned solid loss varies from 0.5 to 1.5. The radiation and incomplete combustion loss is approximately by 0.5%. Incomplete combustion loss means carbon in the bagasse is not burned completely to carbon dioxide, but it is in the form of carbon monoxide, and in this case only 35% of the energy is released, 65% energy goes to the flue gas due to this formation of carbon monoxide instead of carbon dioxide. So this depends upon the excess air ratio. Also, the retention time of the gas in the furnace, this relates to the unburned solid loss. So all these total losses are considered here, and the available energy is net calorific value minus these losses divided by the gross calorific value. So this figure comes to 71.38. But the boiler manufacturer never gives the guarantee of this. They have a margin of 1%. So here the boiler efficiency is worked as 70.38%. Next. Then the process steam demand is considered as a 30%. So on this 30%, the steam demand is 68 tons. The HP heater requires 11 tons. That another the first extraction is called as the HP heater. Second extraction is called the LP heater. LP heater demand is about 18 tons. The deaerator steam is 6 ton. Condensing route is 48 tons. So the total steam generation is 147. Here, it is considered that the cogeneration plant will work only in the season. Total bagasse will be consumed or used as a fuel during the season only. Because of this, the boiler capacity increases, the condenser load increases, I have worked for this pure back pressure and double extraction back pressure, and the comparison is also displayed in the last sheet. The blowdown is considered as a 1.5%, and because of this 2.2 tons of water is lost, and the feed water is 148 tons and power steam generation is 147 tons. Then the process steam requirement as a third extraction, the steam required for the process is designed for 1.5 kg back pressure, but operation it may be 1.2 bar, and the there is a pressure drop of 0.2 bar from the turbine to the process evaporator, and the approximate the average pressure to the evaporator is considered as 1 bar. So this from this Excel sheet, these figures are worked out. Today I have some vision problem. I can't read these things clearly. Even the glasses can help me. Next. The boiler 110 kg pressure boiler is considered. The temperature of the steam is considered as 540, and enthalpy of the steam is 828.
जेवढं समजू बोलायचं तर माईक घेऊन बोला. माईक
Mic.
माईक हां हां जेवढं समजा म्हणजे दिसेल तुम्हाला. हां ठीक आहे हो घ्या जेवढं पण घ्या.
The pressure drop in the superheater is considered as 5 kg. So the drum pressure will be higher than the outlet pressure of the steam. So drum pressure will be 110 plus 5, 115. And due to this high pressure steam in the drum, the saturation temperature for this drum pressure is 321. The steam generation is 147.48. Water consumption is 49.39. And the steam to bagasse ratio, we have calculated the further slide. It is a 2.692. Steam to bagasse ratio for this 110 540 degree steam is with a boiler efficiency of 71%. The steam to bagasse ratio is 2.692. This is only due to the HV heater. The bagasse requirement is 54.7 tons with this steam to bagasse ratio. Bagasse saving per hour is 3.4 tons, and the surplus bagasse is about 1.4%. Operation of plant is 160 days. The calculation of HP heater. The temperature in the steam turbine is 321. the economizer outlet temperature should be less by 30 degrees, so that there should not be formation of steam in the economizer. So the margin is 30 degrees. So 321 minus 30, economizer outlet temperature should be 291. Then temperature rise in the economizer is 70 degrees centigrade. This is assumed because I have considered 100 degree temperature loss in the flue gas. The temperatures drop about 100 degrees to have a rise in economizer by 70 degrees centigrade. The inlet temperature of the HP heater is 221. So this is the figure due to which the steam to gas ratio is 2.692. This is the outlet of the LP heater. Temperature rise in the LP heater is 40 degree. Inlet temperature to the LP heater is 181. Outlet temperature of the LP heater is 181, and inlet temperature of the so the temperature rise in the HP heater is 40 degree, and temperature rise in the LP heater is 68. Here the efficiency of the power generation of HP heater is on lower side. Because of this, the temperature considered in the HP heater is on lower side. However, the in the LP heater efficiency is more, so the temperature rise considered on higher side, that is 68 degrees, and the deaerator temperature is 140. Next. So these are the calculation for HP heater. The outlet temperature of the HP heater is 221, and to heat the water to that temperature, the temperature of the steam must be 10 degree higher. So the inlet temperature of the steam, saturation temperature of the steam from the first extraction should be higher, and that saturation temperature is 231, and corresponding pressure from the steam table is 24, and there is a pressure drop from HP heater to from turbine to HP heater 1 kg. So the turbine outlet pressure should be 25. The pressure, the temperature drop from the turbine to HP heater is considered 5 degree centigrade. So that there is an increase in temperature to 27, and here this is the saturation temperature, and 110 is the degree of superheat, because the efficiency of this first extraction is lower, and because of that, instead of 227, the temperature outlet from this first extraction is 337, and because of that, the specific consumption of this HP heater is on lower side. The enthalpy is 740. So with this system, the steam required for this HP heater is worked out, and that is 10.37 tons. Next. This is a calculation for LP heater. Outlet temperature of LP heater is 181. Again, there is a temperature rise of 10 degree for the heating of steam, and saturation temperature is 191. And similarly, this is worked out, and here the degree of superheat, instead of 110 in HP heater, here the degree of superheat is 55 degrees, and because of this, the efficiency is increased, that is reflected in the power generation, and steam consumption is increased to 16.2. Next. The calculation for deaerator. The deaerator receives water from HP heater, LP heater, deaerator steam, process steam, condensate from condenser of TG set, and makeup water. And all these temperatures are known. The HP heater condensate comes to the LP heater, and from LP heater some flash heat is recovered, and it comes with HP heater and LP heater to the deaerator. If we go for this double extraction back pressure turbine, in that case, this temperature of this HP heater, LP heater and sugar process is more than sufficient, so no deaerator steam is required. But here, due to this makeup water and the heat recovery, this about 6 ton of steam is required for the deaerator. The total steam generation is known. Considering the blow down, the total water requirement that is known, and from this total heat divided by the flow water to the feed water to the boiler, the temperature of deaerator is 140. Next. Then the parameters of this TG, there is a pressure drop of 3 degree from boiler to turbine. So the inlet pressure of the turbine will be 107 bar, and the temperature drop of 10 degree. The temperature of steam at the inlet of the turbine will be 530. The first extraction is at 25 bar. Second extraction is a 10 bar, and this is the enthalpy of the inlet to the turbine. The efficiency of the TG set is a 95%. The efficiency, mechanical efficiency of the turbine is considered as 99.5. Efficiency of the gearbox is considered as 98%. Alternator mechanical efficiency is considered as a 99.5. And alternator electrical efficiency is considered 98%. So overall efficiency of this set is considered as 95. Then turbine inlet steam parameters. So these are the repeated things here. So the enthalpy of the turbine at the inlet is 123. Inlet pressure is 107 and inlet temperature is 530. Next slide. Then power generation by HP heater, LP heater, deaerator and process steam. The inlet enthalpy and outlet enthalpy of HP heater, the difference is 83 kilocalories per kg. The steam flow is known, so from this we can calculate how much power is generated, and this is 1005 kW. This is from HP heater. From LP heater, here the heat recovery is increased from 83 to 127. So because of this, specific consumption is reduced, and here some steam is increased, but the efficiency is also increased. So the power generation is 1000, increased from 1005 to 2273. Then for the process, the enthalpy at the outlet is known. Here the gain in reduction in the enthalpy is 173. Here it is 83 at the HP heater, at the LP it is 127, and the process it is 173. And because of this, the power generation is 1400 watt 73, so about 14 megawatt power is generated here. 2 megawatt power is generated at the LP heater, 1 megawatt power is generated at the HP heater. At the condensing, the absolute pressure of the exhaust steam is 0.1, saturation temperature is 45, and about 49 ton of steam is passing to the condenser, and the power generation is 14.3 megawatt, and total power is about 31.7 megawatt. So total power generation is 1005 plus 2273 plus 14.173 due to the process, 14.31 due to the condensing, and total power is 31.758. This power generation is known, steam flow is known, the specific consumption is about 3.8. Now about 10% of the power is required for the boiler and turbine of the total generation. So this is 31 megawatt. So out of this 10%, 3 megawatt power will be required for the boiler and TG set. 25 kWh per ton of cane is considered for the sugar process, and the power requirement for the sugar process is 5881 kW. Total power of the process power plus the power required for the Cogen plant is 8857 kW, and this total power of 31 megawatt minus this 8.8 megawatt, available power for the export is 22.8 megawatt. The total unit generator per ton of cane is 139.7, and the exportable power is 100.8 kW per unit. 100.8 unit per ton of cane. To power generation is 139.7 unit per ton of cane, and power consumption as a captive power is 39 kW per ton of cane. Next. So this is the bagasse balance. The enthalpy of the required for this evaporator is 643 with 120 degrees centigrade. The about 120 kilocalories going to the condenser. So net heat absorbed by the evaporator is 523. The steam quantity is 68 tons. The steam to bagasse ratio is 2.6.
Borude sir, I just request you just give us a gist. Detailing is not necessary because this can be given to anybody who wants to.
Yeah.
Okay. There is no issue.
Okay.
So only gist can be told what is the efficiency and what are the overall, because the timing is up.
Yeah.
And you have to have some
Only
questions.
main points you can highlight.
My submission is let everybody have this paper and everybody have this earlier paper with everybody, because it is a role model and it is like a bible to a sugar industry for heat and mass balance. And we can always have, you can contact our office, they will just send it to you a soft copy. Just tell us a summary, let's complete.
Main points you
Here,
can highlight.
here the bagasse consumption per unit power generation is a 0.783. 0.783 kg per kg of per unit. But here, this figure is 0.738 is on higher side, almost double than the back pressure unit. Back pressure unit requires only 0.37 kg per kg of per unit. 0.37 kg per unit. Here, the efficiency of the sugar plant and the cogeneration plant is 49.55. This efficiency is on lower side due to this condensing turbine. Generally, if this turbine is a back pressure or double extraction back pressure without condenser, then the efficiency is above 68%. Thermal power stations has a cycle efficiency of 38 to 42%. So, as compared to thermal power station, our efficiencies are better. Here, this is a comparison. The first case is a back pressure, second is a double extraction back pressure, and the just we have discussed is the triple extraction condensing. The bagasse available for each case is a 58 tons. Boiler efficiency is 70.38. Boiler efficiency is independent of the steam flow, independent of the steam parameters. This depends upon the only thermal efficiency of the bagasse system. The bagasse required as a fuel for the pure back pressure is a 63 tons. For the double extraction back pressure is 82 tons, and for triple extraction condensing is 148 tons. This is considered the total bagasse is used during the season only. So the installed capacity in the first case will be 80 tons, in the second case it will be 90 tons, and in the third case is 160 tons. The steam to bagasse ratio is important here with this. What is the temperature inlet to the economizer? In this pure back pressure, the inlet temperature is 14 degrees centigrade. In the double extraction back pressure, the system is same, HP heater, LP heater is there. So the inlet temperature is 221, here also 221. This is here the for back pressure turbine, the steam to bagasse ratio is 2.3, here 2.7, 2.7. So there is a benefit of HP heater, LP heater. The bagasse consumed, see here the figures, bagasse consumed in the back pressure is 30 tons, here also about 31 ton. So hardly 1 ton increase in bagasse because of this. The temperature is increased from 114 to 221. So bagasse consumed is demand is a 30 ton, 31 ton, and 58 tons. So PG set installed capacity here the power generation is 13 megawatt, so installed capacity is 14 megawatt. Here it is a 14.6 megawatt. Installed capacity of PG set is 16 megawatt. Here the power generation is 32 megawatt. Installed capacity is 33 megawatt. These are the captive power. There is a small difference in increasing order here. Only 1 megawatt is power is increased. The percentage of power power required for the boiler is increased. So the specific consumption, this is a exportable power is a 28.7 kW per ton of cane. In the double extraction, it is 35 ton, and in the triple extraction, it is 100.4. So exportable power is on higher side due to this condensing load. This figure is percentage bagasse saving, not TPS. This is percentage. Bagasse saving is 14.3%, or 12.3%, 12%, and here 3%. Sorry, this is 1%. This is TPS. Here the bagasse consumption per unit electrical power is 0.37 kg, 0.37 kg and 0.784. Here the bagasse consumption is increased due to this condensing load. The cycle efficiency of the sugar plant and cogen is 68%, here also 68%, and the triple extraction condensing is 49%. Thank you.
Thank you very much, sir. It's a lovely explanation, and we do expect better than this next time, sir.
Okay.
Once again, the submission is these two papers. They are really good papers. They have done very detailed calculations. We have Excel sheets available with us. Those who are interested, they can always approach office and get the Excel sheet from you, wherein you have to write your variables where the answers will come directly.
A very nice presentation, a studious presentation by Mr. Borude. Since we are behind the schedule, very brief interaction I would like to ask from the audience, if there is any question. Especially Mr. Shrikant Shinde of Cogen India Limited, any expert opinion on this heat balance? Mike.
Is it best presentation? And since long back, this discussion on whether this is required back pressure or whether it is required double extraction tendency, the issue was going on. But according to me, what's happened actually? The back pressure turbine is only used during the season, but condensing turbine, double extraction condensing turbine can be utilized during season as well as off season. That is the beauty of this. Another thing is that only during season, the minimum requirement of 10% steam is required for the condenser. Not more than that. This is the thing. Actually, whatever amount of 10% we are sending to the condenser, this is only because of there is a cooling tower and all of these things. The loss is there definitely. If you want to utilize the turbine during off season also for the power generation, then it is a beautiful thing. Second thing is that when suppose the steam requirement reduces, then because the steam consumption is suppose you reduce from suppose 35% to 25%, then 10% steam available. What can we do for that? If you give to the condenser, then another option to get the income from that. This is there. That is my opinion.
Okay. Thank you. Thank you, Mr. Shinde, for your expert opinion. Please. Very nice presentation. 1 minute. I would like to request Chairman to felicitate. Okay.
This is Mohan from Dynamic Oil. I just want to comment on power generation balance efficiency. You consider for overall system. You have considered the system efficiency of means power generation 95%, 99.5%. 98% efficiency of gearbox and 99.5% efficiency of alternator. generally speaking, gearbox efficiency, especially high-speed gearbox, when you are not running it at a full torque, means design torque, its efficiency drop down drastically. Means for an example, it is designed to deliver a torque of 16 Newton meter for high speed. It will not deliver if it run at 8 Newton torque. So overall efficiency, normally for the calculation, if you consider 95% and if it comes 92%, the total heat balance will be really changed. So I think regarding the efficiency, we should be very careful while considering. Also, alternator efficiency 99.5%. If you see motor, any motor rotating electrical generation system, they have claiming maximum efficiency of 95%. So 99.5% alternative efficiency, mechanical efficiency looks to me very high.
Thank you, Mr. Patil. There should not be any change in the efficiency of the gearbox, whether on full load or no load. Only 1% heat energy loss in the stage, and there is single stage turbine gearbox. So, and the about 0.5% energy is lost in the bearings. So, 0.5 to 1.5 or 2% is the maximum efficiency loss in the gearbox. There is no relation with the loading. The alternator, alternator has two efficiencies. One is the mechanical efficiency, which is consumed at the bearings, that is 0.5%, 0.5% loss, and 2% as an electrical loss.
Thank you. Mr. Mohan Patil has very rightly raised the issue of a torque factor in energy balance. Nice. Okay. I request the chairman to felicitate the speaker. Be seated. Now, in a pre-lunch technical session, this last paper by Mr. Binu Panikar, who is the Vice President of Raj Process Equipment and Systems Private Limited, Pune. He is going to make presentation on heat and mass balance case study of a distillery plant. Time limit will be 30 minutes. About 20-25 minutes for presentation, 5-10 minutes for interactions. Okay. This is a very brief introduction of the speaker. He is a graduate in mechanical engineering and with vision of perseverance achieving goals. He is working as a Vice President of Marketing and Sales in a reputed organization named Mr. Raj Process Equipment and Systems Private Limited, with a quest to achieve highest quality in products and customer satisfaction. He has a